Okay, so welcome back. So today we are going to start with the casting and process modeling. So out of that, I mean first module. Now today in this class we will discuss about the basics of casting and solidification, and we will try to learn about how we basically achieve solidification from liquid metal to solid state. I mean what is the basic fundamental principles of it, and how I mean we can achieve the desired level of structural integrity, and also the mechanical properties, physical properties in the solid. It can be metal, it can be composite. So, so that everything depends on the mechanism how we are basically achieving the solidification. And then once we understand the basic nuances of solidification processing, we will discuss more about the how to engineer the component for casting process, how to design the die cavities, what are the fundamental principles of casting processes. So, we will learn all those in this class. So let us start with the origin of metal casting processes. So, metal casting is a very basic and fundamental process that has been originated long back in probably around 3500 before Christ in Mesopotamia, and so it is ancient in a sense that there are examples, there are noted history, there are it is written that there are several weapons, tools, ornaments, utensils out of copper and bronze were made during Indus Valley civilization, also adopting casting route. And also in India, so in Delhi you might have seen Qutub Minar and the famous iron pillar, that is a testimony of the metallurgical prowess, the casting process. It is a perfect example which is standing tall. It is a 7.2 meter long this minar or pillar. So, it is made of pure malleable iron. So, it is an example of casting process. So now after we discuss the origin of metal casting process, now we will discuss about the different casting processes, and we will also talk about their advantages, limitations. So, like sand casting is one of the most basic casting process that has been being utilized for several decades now, and it is basically very much useful to develop large size objects, ingots for secondary processing, and also for components for usage in several industries like railway, like power plants, like mining, and several examples of such are available. So, the advantage is sand casting technique can be utilized for almost any metals, can be cast using sand casting techniques, and it is dealing with low equipment cost, and it is also very economical process. But the limitation is its coarse finish, and also dimensional accuracy is not proper, and also the surface finish sometimes it is not up to the mark, and that is why we often need to keep a significant amount of machining allowance when we are dealing with the sand casting route. So, and then here comes the investment casting, which is one of the most accurate casting technique in terms of achieving dimensional accuracy and also very improved surface finish. But the limitations of investment casting with there are part size that can be developed using investment casting route is quite lesser, much lesser in dimensions rather than what we can do in case of sand casting, and it deals with expensive pattern and mold and involves significant amount of effort, labor intensive. However, its advantages outclasses, outsmarts the limitations of this process. So, here almost any metal can be cast, it can provide good surface finish, dimensional accuracy, and intricate shapes. So, this is the most important term. So, the intricate shapes. So, that is why investment casting is often utilized for several jewelry, and also I mean there are precision components, micro components, and also it is a widely used technique to develop single crystal castings that we will be discussing later in the course. So there are many I mean potential advantages of investment casting route over other techniques, but every casting technique has their own merit and has their own I mean applicability. For example, permanent mold casting, so mostly we call the gravity based permanent mold casting, and so here the advantages are it is I mean provides good surface finish, and also like in case of sand casting we have to we cannot reuse the mold, like after every I mean casting process we have to basically I mean dismantle the mold, and again the sand ramming I mean all the procedures need to be repeated, whereas in case of permanent mold casting, once we manufacture the die effectively, we can use it for a number of casting cycles, we can develop a number of components with a much better surface finish and also with a much better dimensional control, and more importantly we can achieve much higher cooling rate. And that is why we can achieve I mean lesser grain size in the solidified parts compared to that you can achieve in case of sand casting, and that is why it provides I mean higher improved mechanical property in the permanent mold cast parts compared to that we can get for the same material if we are developing them by sand casting route. So, and here comes the die casting. So, in case of die casting mostly we I mean call die casting as high pressure I mean die casting. So, here we can get excellent surface finish and we can I mean achieve a, I mean much higher production volume, and at a much faster rate we can produce the components in case of die casting, but every technique has their certain limitations. So, in case of die casting it is the I mean high cost of the die, limitation on part size, and also generally it is limited to non-ferrous metals. And another problem is because it is deals with a it's a high velocity process. So, it deals with certain I mean porosity content in the I mean solidified objects. So, and also that is why I mean it is I mean liquidous conventional high pressure die cast parts are not heat treatable. So, that is also another major disadvantage with the high pressure die casting parts. But that is non heat treatability. So, I mean so then we will discuss later in this course how we can tune high pressure die casting in a way with appropriate process and material changes that we can also impart heat treatment to the parts produced by high pressure die casting route. And then next is in the line is centrifugal casting. So, centrifugal casting is also I mean very high production rate it offers with good dimensional accuracy, and here the structural integrity comes from the centrifugal force with which the melt is thrown towards the periphery of the mold. And so a perfect example of centrifugal casting is the hollow ductile iron pipes that we can manufacture by centrifugal casting route. So, like in the country Tata Metallics is one of the largest producer of this hollow ductile iron pipes that are being used for I mean several industrial applications. Like transports for fuel, gas, and so on. So, that I mean is an example of centrifugal casting utilization, but the limitations with centrifugal casting are expensive setup, good for production of cylindrical parts only. So, and then with this we have discussed about some important I mean casting processes. So, now we will discuss about the different kind of molds that we generally use for I mean casting melts. So, the mold material varies from sand to metal. Like I already told you, when we are dealing with permanent mold casting, we do use metal I mean metallic molds, and that mold can be made of cast iron or aluminum or zinc, and every material I mean mold material has their own unique advantages and disadvantages. And so I mean and also based on the mold material which is being utilized, the tooling requirement I mean the tooling cost also I mean varies with that. Like for example, in sand casting there is not no tooling cost at all, and when we are using permanent mold casting out of say aluminum, then it is much easier to machine because it is a ductile material. However, when we are using die steel or high strength steel as the die material or mold material, that time the machining cost also increases accordingly. So, so then we basically need to choose the mold material based on the number of parts that we need to manufacture. That means how many casting cycles that mold need to endure, it need to undergo, and also it depends on the at which temperature we are casting, what is the requirement in terms of thermal conductivity of the mold material, so on and so forth. So, here there is a summary which is done presented between different mold materials and the type of metals cast using the individual mold materials. So, with this now we are going to show you the some basics of the this getting arrangement and die geometry within the mold cavity. So, this is an example of a typical mold cavity. So, you can see there are several functional parts. So, here this is the pouring cup or basin, and this is the down sprue, and then this is the sprue base well, and so sprue base well, and this is the runner, and here it is entering into the component cavity. So, this is basically the ingate, and this is the core, because we need to make a hollow cavity within the part that is getting solidified, being manufactured by the casting technique. So, that is why to get the hollow cavity we are using this core, and the mold consists of two halves. The top half is called cope, and the bottom half is called drag, and the line which separates both of them is called the parting line. So, and here this is an example of a riser which is a blind riser, we will learn later. So, for now I will tell you the function of riser is basically to feed to the solidification shrinkage. That means, because of the density difference, because of the higher density of the solid state of the most of the materials compared to the liquid state, there is a density change happening, and that is why there is a tendency to shrink, and to this riser is necessary. It is a reservoir which is basically kept to feed to that solidification shrinkage, so that we can achieve the cast part within the desired dimensional attributes. So, so here this is an example of a connecting rod, automotive connecting rod, which is shown for your ease of understanding, which is getting manufactured by casting route. So, here you can relate it with this. So, here all the functional parts of the getting geometry are marked over here, and here there is an example of top riser is also given, which is so which is on the, so in connecting rod you might have already studied. So, there are basically two ends, one is a big end pin, one is a small end pin. So, in the big end pin where the cross sectional area is higher, the top riser is basically placed, and here this is a perfect example of a multi cavity casting. So, you can see at one go we are basically solidifying multiple components. So, 1, 2, 3, 4, 5, 6, 7, 8. So, we are getting 8 components out of one casting cycle. So, this is a example of a multi cavity mold that we can use for casting number of parts at once. Okay. So, with this now we have understood that how we basically do the casting process. So, now we need to learn about what is the fundamental physical principles involved in the phase change process in casting, that means liquid to solid transformation. So, in case of pure metal at fusion temperature delta G is 0. So, basically how it happens. So, this is basically the free energy versus temperature curve. So, this is the temperature and this is the free energy G. Okay. So, assume that here this is the melting temperature Tm. So, beyond the melting temperature, free energy of liquid is basically lesser than that of the solid. So, this is the free energy line for liquid, this is the free energy line for solid. So, at melting temperature, so the basically the free energy, that is free energy change delta G, for example, this is Gs minus GL. So, this is the driving force for solidification. So, at this melting temperature, equilibrium melting temperature delta G, what is the value of delta G? Delta G value is 0. So that is why I mean, so here this is the equilibrium state of matter, and if we increase the temperature further, so then the I mean it will be it will be prone to go towards liquid state, because free energy of liquid is lesser, but that is not the case when we go below the equilibrium melting temperature. So, in that case we will see the free energy of solid is lesser than the free energy of liquid. So, that is why there will be a transformation from liquid to solid state as we fall below the melting temperature, equilibrium melting temperature. So, in case of pure metal at fusion temperature, that means this is Tm or Tf, you can call it as Tf in case of as fusion temperature. So, delta G is equal to 0, that is what I have shown you over here. So, that delta G is equal to delta Hf, that is the fusion enthalpy change, minus Tf fusion temperature, delta Sf, that means the fusion entropy change, which is equal to 0. That means delta Hf is equal to Tf delta Sf. So, here delta Hf is the latent heat of fusion, delta Sf is the entropy for fusion. So, for any temperature other than Tf, so this expression becomes, so delta G is equal to delta H minus T delta S. So, because delta H is equal to the latent heat of fusion always, and delta S is equal to the entropy for fusion. So, we can rewrite this expression as delta Hf minus T delta Sf. So, as we know from this expression that delta Hf is equal to Tf delta Sf. So, if we put this expression over here, then we get delta Sf, delta Sf Tf minus T, that means delta T. So, this is basically the undercooling. Undercooling means at by how what is the by which temperature, what is the gap between the temperature of the melt at present and between its liquidus temperature or its equilibrium melting temperature or fusion temperature, whatever you may call. So, that is the gap. So, that gap is called delta T, the undercooling. So, the driving force is therefore proportional to the undercooling, provided that the latent heat and the entropy of fusion do not vary much with temperature. So, this is basically the driving force for solidification. So, now we are trying to learn the fundamentals of the casting process that we have just discussed before in this class. And so, consider a simple transformation. So, as I have already shown you, so where a liquid L transforms to crystals of beta. So, this is possible only when delta G is negative. So, delta G sign will determine the direction of phase change. Okay. So, here G beta minus G L less than 0, G beta is the free energy of the solid, that means it will move from liquid to solid direction, that means liquid to solid phase change will happen. So, just below the equilibrium temperature, that means somewhere here the magnitude of the free energy change is very proceed, and the reaction can proceed slowly, whereas with a large supercooling below Tf the reaction proceeds much faster. So, it is talking about, so when we are just here, so then the transformation rate will be slower, and if the say the large the supercooling is available, that means the temperature of the melt at that given instant is much lesser than the equilibrium fusion temperature, that is Tf, then the transformation will be much faster. We will learn in the subsequent slides. So then the solidification mechanism is basically the combination of two micro mechanisms, one is nucleation and another is growth. So, nucleation, it is the tiny product particle, I would say solid particle, which is coming out from the liquid melt, and then based on certain conditions, based on its free energy, based on the critical radius for nucleation for that particular metal, for that particular solidification condition, it determines whether that nucleated nuclei will survive or it will dissolve back within the melt. And if it is surviving, then it is it shows tendency to grow. So, that is the growth phase of the nuclei. So, the physical process by which a new phase increases in size is called basically the growth. So, when a particle is formed, a new interface is created between the particle and the liquid, and like all surfaces, this interface has a positive energy. So, which must be supplied during the transformation, I mean liquid to solid transformation process. So, assume that we are basically nucleating a spherical particle from the liquid melt pool, which is say for example kept within a container, that is shown like this over here. So, then these spherical particles are coming out from the liquid melt, the tiny nuclei. So, then if in case of in their case, so the surface area by volume will be the sphere surface area, that is 4 pi r square divided by sphere volume, that is 4 by 3 pi r cube. So then it becomes is equal to 3 by r. So, as r tends to 0, energy of the surface prevents initial formation of a tiny particle. So, that means if the nuclei is very small, I mean r tends to 0, so then its surface energy prevents its initial formation, and so the chill zone contains the fine crystals nucleated at the mold surface. So, it is another concept. So, here, so this is an example of a mold. So, it is an example of a directional solidification. How? So, this is for example, this is a metallic mold. So, then it provides a chill zone to the liquid melt, which is allowed to solidify within this mold. So, at the chill zone you will find some equiax grains, and after the chill zone, so there will be columnar growth of the solidifying melt in case of pure metals. So, why this is happening? So, basically this is the direction of heat removal, and so heat is getting extracted from the melt from this direction, because the metallic mold we have assumed it has a high thermal conductivity, and so the dendrites grow opposite to the direction of heat removal. So, that is why we can see the direction of growth is in towards the center of the ingot. Okay. So, so if the liquid in the center of the mold is undercooled sufficiently, there may also be equiax grain forming. So, this condition speaks of according to this positive thermal gradient, where in solid temperature is less, at the interface it grows towards the interface, and from interface it increases within the liquid, which is a suitable for columnar growth. So, you can relate it to this. But there are cases where beyond the interface, this is the solid liquid interface. So, beyond this interface the temperature drops within the liquid. So, that time we see perturbation to the growth, and we end up getting negative thermal gradient, which results in equiaxed growth of the solidifying grains. So, this is what is shown over here. So, this is because of the negative thermal gradient ahead of the interface, solid liquid interface. So, equiax growth in a pure metal shows morphological instabilities. This is because a small perturbation at the interface ends up in even more supercooled liquid. So, the interface becomes unstable. So, now we will discuss about the case of homogeneous nucleation. So, here in case of homogeneous nucleation, so in this case so there are basically nucleations are of two types, one is homogeneous, one is heterogeneous. So, in case of homogeneous nucleation, the tendency of nuclei formation throughout the domain is same. But in case of heterogeneous nucleation, we basically add some preferential sites or impurities or grain refining modifying agents within the melt, which provides as preferential sites for nucleation of the evolving primary grains. So, this is the major difference between homogeneous and heterogeneous nucleation. So, talking about the homogeneous nucleation, so let us assume a small volume of liquid Vs turns into solid. So, assume this is the small volume of liquid Vs and this is the total liquid volume Vl, and so if Gs is the free energy per unit volume of the solid and Gl that of the liquid. So, if ALS is the solid liquid interfacial area, and if delta SL is the interfacial free energy, then the total free energy of the system is given by Gf, this is the final free energy of the system, is equal to Vs into Gs plus Vl into Gl plus gamma Ls ALS. Gamma Ls is the surface energy of the evolving tiny solid particle, and this is the surface area of the liquid solid interfacial area of the tiny solid particle that is originating from the liquid melt. So, before the small volume of solid formed, the free energy of the system is given as G initial, which is Vs plus Vl, the total volume, into GL, free energy of the liquid. So, thus the total free energy change associated with the transformation of a small volume of liquid Vs into solid is given by delta G. So, delta G is equal to G F, G final minus G initial. So, is equal to this expression. So, Vs Gs plus Vl Gl plus gamma S Ls Ls into A Ls minus Vs Gl minus VLGL. So, then VLGL and minus VLGL cancels out, and then if you take Vs common, then Vs bracket Gs minus GL plus gamma Ls A Ls. So, then Gs minus GL is nothing but delta G, what we are writing in the next expression. So, the total free energy change small delta G is equal to Vs capital delta G plus gamma Ls A Ls. So, now considering formation of a spherical new phase particle, we get delta G, that is the free energy change, is nothing but 4 by 3 pi r cube, because we are considering it is spherical. So, this is the volume of the sphere. So, 4 by 3 pi r cube. So, this is the volumetric free energy change plus 4 pi r square gamma Ls. So, this is the surface energy of the tiny solid particle which is forming, and this is the surface area of the sphere. So, the critical radius of the solid that is stable when formed in the undercooled liquid can be identified by minimizing delta G with respect to R. So, then if we just do the differentiation with respect to R of the free energy change delta G, that means ddR of delta G at R is equal to RC, then if we do the differentiation and then at R is equal to RC, if we equate it to 0, so, then we after rearranging the terms, we can get that RC, that is the critical radius of nucleation, is equal to minus 2 gamma Ls by delta G. So, gamma Ls is the liquid solid interfacial area by total free energy change delta G. So, so this is how we can get calculate the value of the critical radius for nuclei for a given delta G value. So, one can calculate the delta G at RC. So, that means the free energy change at critical radius of nucleation we can also calculate based on the following expression. So, this expression we have discussed earlier also. So, delta G is equal to delta H minus T delta S. As we know that delta H and delta S does not change much because they are same with the enthalpy of formation, enthalpy and the entropy of fusion. So, so delta G at Tf, Tf is the equilibrium melting temperature or the fusion temperature, is equal to delta H function of Tf minus Tf delta S Tf. So, so delta S Tf, as we know from the previous expressions, that delta S Tf is equal to delta H Tf by Tf. So, because how we are getting it, because delta H is equal to, we know that T delta S. So, delta H F is equal to T delta S F. So, that is why we are getting delta S F is equal to delta H F divided by T F. Okay. So, so this is how we are getting this is how we are getting the value of delta S T F. So, again delta G is equal to, if you now put this value of delta S T F is equal to delta H T F by T F. So, then we can so we can calculate like this. So, then you can see delta S T F is equal to delta H at T F, delta H at T F by T F. So, T F is the fusion temperature. So, then if you take now delta H as common, so then 1 minus T by T F. So, then which becomes equal to T F minus T by T F. So, T F minus T is nothing but T F minus T is nothing but delta T. So, then we can very effectively write delta G is equal to delta H delta T by delta Tf, that means the undercooling, divided by the fusion temperature into the enthalpy change delta H. So, I mean but as we have already known from the previous slide that delta Gc at critical, so that means the total free energy change at critical radius of nuclei is equal to 4 by 3 pi r cube. R is converted as Rc, that is the critical radius of nucleation, because our objective is to evaluate the free energy change value at critical radius of nuclei into delta G, that is the volumetric free energy change, plus the 4 pi Rc square gamma Ls, that is the surface energy of the new product particle which is coming out from the liquid melt. And now if we put the value of delta G over here, so that is delta G is equal to, as we know, the value of delta G is equal to delta H delta T by Tf, and then so from here we can give, first we can put the value of critical radius of nucleation, that is Rc is equal to minus 2 gamma by delta G, that is what we have evaluated in the previous So, this is where you can see this is the value of Rc that we have determined by differentiating delta G with respect to R and equating it to 0. If we put that value over here, so then we can get Rc is equal to minus 2 gamma by delta G. If we place here, then finally we are arriving at this expression, that is 16 pi gamma Ls cube by 3 delta G whole square. And we can further simplify it if we are putting the value of delta G that we have calculated over here. So, then how it becomes 16 pi gamma Ls cube divided by 3 delta H square delta T square by Tf square. So, then we are getting 16 pi gamma cube Tf square divided by 3 delta T square delta H square. So, this is the final expression of delta Gc that we are getting, that is the. So, we now have evaluated the critical radius of nucleation, we have also evaluated the free energy change at critical radius of nucleation. So, this is this is how we have now, and from this curve you can understand that the critical radius of nucleation is decreasing with the decreasing temperature of the liquid melt. Why? That means it shows that because the temperature of the melt is lesser, means it has higher delta T value. So, you can also get it by calculation. So, higher delta T value makes a smaller Rc value to be stable. That means, a smaller nuclei can become stable and it can grow to become fully formed grain. So, that is why as we are decreasing the temperature of the melt, like T2 lesser than T1, T3 lesser than T2, and similarly the critical radius of nucleation R1 R2 less than R1, R3 less than R2. So, this is how it goes. So, this is the fundamentals of the homogeneous nucleation, and so there is a small example problem so that you can understand the calculation better. So, so this is calculate. So, for example, calculating the critical free energy of nucleation of ice from water at 0 degree centigrade, at minus 5 degree centigrade, and at minus 40 degree centigrade. Also calculate the critical radius at each temperature. So, the enthalpy of fusion of ice is 6.02 kilojoule per mole so, the energy of the ice water interface is 0.076 joule per meter square. So, do not get confused, it should be meter square, can be taken to be independent of temperature. So, at 0 degree centigrade there is no supercooling, that means delta T value is 0. So, there is no critical radius, because without undercooling, as we have just learned that we it is very difficult and it is impossible to basically formation of the tiny nuclei, because the free energy change at will be infinity. Okay. So, then the 0 degree centigrade case is ruled out, and then in case of minus 5 degree centigrade, that means there is a undercooling of 5 degree. That means, as we all know that in case of ice, I mean equilibrium water and ice temperature is 0 degree. So, if we go below 0 only, then only liquid to solid, I mean water to ice transformation takes place. So, so the degree of undercooling varies. So, in case of minus 5 degree, that is the 5 degree centigrade undercooling, taking the molar volume of ice as 19 semi cube. So, then we just need to put the formula of delta G C that we have evaluated in the previous slide. What is that formula? We have evaluated as this. So, 16 pi gamma L s cube by 16 pi gamma L s cube by 3 delta G square. So, this is what we are putting here. So, 16 pi gamma L s, that is the I mean surface energy L s cube by I mean so like we have seen this by 3 delta G square. So, here you can see 3 delta G square. So, delta G is basically that is the enthalpy of fusion 6.02 kilojoule per. So, we have to convert it to joule per mole, that is why we need to multiply by 3, that is what we have done. And then here, because 19 semi cube, so we need to convert it to meter cube. So, we need to multiply it by 10 to the power minus 6. So, that goes at the top and gets multiplied with 6020. So, then into 3 into delta G square, when delta H square into, I mean this is the critical radius, I mean sorry, this is the undercooling delta T, I mean so that is the 5 degree centigrade. So, 5 square. So, end of the, so finally we are arriving at the value of the critical free energy change as 2.2 into 10 to the power minus 16 joule. And then we know that we have evaluated the formula for the critical radius of nucleation as minus 2 gamma by delta G. So, here you can see that we are basically evaluating. So, then 2 into I mean 0.076 that is the I mean the energy of the ice water interface, and divided by the I mean. So, this is the minus sign, you can see this is the minus sign is shown over here, into delta G, that is the similar reason. So, we need to I mean convert this the molar volume semi cube to meter cube. So, finally, we are arriving at the expression for I mean the critical radius of the product particle, which is 262 Armstrong. So, it is interesting that when we are that so this proves my previous statement that I have discussed in the last slide. So, as we are going further down in temperature, now we are going to minus 40 degree centigrade. So, then the I mean a much lesser critical radius of nuclei will remain stable. So, that is what is evident from here. So, in this case the critical radius of nucleation is only 33 Armstrong, which is much lesser than 262 Armstrong. So, this is how the homogeneous nucleation prevails. So, with this we are stopping in this class. In the next class we will start with the discussion of heterogeneous nucleation, and also we will discuss about some of the thumb rules, how we can achieve a casting with sufficient structural integrity and the desired quality of I mean thermophysical and physical attributes. So, thank you.